Hey, hello, and good morning or good afternoon, everyone, and welcome to the 53rd annual Division for Planetary Sciences meeting. Um, this is the second day of press conference. I'm Shantanu Naidu. I'm the DPS press officer, and today with us we also have Rick Feinberg, who's the past AAS press officer. We have Susanna Kohler, who's the current AAS press officer, and Kerry Hensley, who's the deputy AAS press officer. For those of you who could not join us at yesterday's press conference, we have all the press releases and the presentations and video of yesterday's press conference on the meeting website. If you click on the press information and then the press kit, you can find that there. So before we begin, a few ground rules. We'll be recording this briefing and streaming it live on YouTube. I will begin by giving a brief introduction to everyone's topic and the presenters, and then all the panelists will speak in order, and then we'll go to the Q&A. If you wanted to ask a question, you can type your question using the Q&A feature at the bottom of the Zoom interface. And please be sure to type your affiliation and which presenter your question is for. You can upvote other people's questions to raise their priority in the queue. We've asked the presenters not to answer questions via text while other presentations are still going on. We will answer them aloud during the Q&A session. And if attendees wanted to chat with each other, they can always use the press_conferences channel on Slack. Okay, so with that, we'll have 4 topics today, 5 presenters. We'll begin with Wesley Fraser from Herzberg Astronomy and Astrophysics Research Center. We'll talk about Col-OSSOS, the BrightIR and FaintIR taxonomy for Kuiper belt objects. Next, we'll have Maitrayee Bose from Arizona State University. We'll talk about the possible connections between an unusual micrometeorite and dwarf planet Ceres. Next, we'll have Cristina Thomas from Northern Arizona University. We'll talk about Lightcurve observations in support of the DART mission, understanding the orbit of the Didymos-Dimorphos system. And next, we'll have Emily Deibert from University of Toronto, along with co-presenter Jake Turner from Cornell University, and they'll talk about the exotic atmosphere of an extreme world, detection of ionized calcium in WASP 76b. And so with that, I'll let Wesley Fraser take over.
Just sharing screen and, wrong button. There we are. You can all see that, I presume. Hi, everyone. Thank you for coming and listening to the latest and greatest on Col-OSSOS, specifically about, as Shantanu said, the new taxonomy we've developed for Kuiper belt objects. We're certainly not the first to have attempted to develop a taxonomy in the past. There's actually about a 2-decade history in trying to do this. And the story usually goes something along the lines of gather a bunch of optical and near-infrared colors of Kuiper belt objects, and then either look for clustering in clusters of clumps, basically, of objects with similar colors in the color space, or apply some relatively fancy statistical techniques like principal component analysis that break down that color space and then look for clumps in that color space. And I've did this with Mike Brown with the hot sauce survey. The Antonella Perucci's got a long history in this. But regardless of who does it and how you, depends on how you slice and dice things, you can come up with anywhere between 3 and 10 different classes of Kuiper belt object. And this has always really annoyed me because it's actually more than just counting. We're actually constraining the protoplanetesimal disk from which Kuiper belt objects came. So here's a very simple diagram depicting this. We know that the source of the surfaces that we see in the surface types reflects directly on the compositional divisions in the early protoplanetesimal disk before Neptune migrated and sculpted the Kuiper belt we see. And so if you see three different classes, for example, then you know that there are at least a couple compositional dividing lines, whether they be ice lines or sublimation lines, that created the different surfaces we see, quite analogous to different types of asteroid. And so it's actually really important to know how many types there are. But even more than that, you can get a lot more specific. What I'm showing here is the orbital element distribution, eccentricity, inclination, and semi-major axis of the so-called cold classical region of the Kuiper belt. These are objects that are usually considered very red and very shiny. And so they're often considered their own class of Kuiper belt object for that reason. And if you take a look at their colors, we now know that there are a few cold classicals that have what we would consider a neutral reflector surface type. And so that's the blue points on top of the otherwise regular red cold classicals. And the reason why this is important is because we now know those are actually push-out survivors of Neptune's migration. And so there's a specific type of migration that occurred that picked up these objects from much closer regions of the sun and dropped them into the cold classicals. And so if you can identify the outliers in different regions, then you can actually use them as dynamical tracers. For those of you who haven't heard of Col-OSSOS, this is Colors of the Outer Solar System Origins Survey. We basically are gathering UV optical and near-infrared colors of about a bit more than 100 OSSOS targets. We've observed 97 at this point, OSSOS being the Outer Solar System Origins Survey. And we've tuned a whole bunch of things to basically gather very good colors for Kuiper belt objects in a brightness limited survey. It's the first ever for that. If you want some details, I highly recommend you take a look at Schwamm et al. 2018, or of course, come talk to me. This is a pair of the main colors that we're gathering for the survey. In the bottom, I've plotted Sloan G minus R. This is basically an optical color, measures how red a surface is, versus R minus Z and R minus J, two near infrared colors, Z being at 0.95, just longer than the human vision, and J at 1.2 microns. You can see all the black points there. Of course, those are the Col-OSSOS measurements and very small error bars, which I'm really proud of. The yellow star is a solar color for reference, and that black curve is what we call the reddening curve, or the curve of constant spectral slope. And so if you're on that curve, you have a linear spectrum that has basically a straight line with a given slope all the way through the bands in question. And this curve kind of has been haunting me a bit, because as you can see, Kuiper belt objects have a tendency to fall along or just below that curve. And that's actually true of pretty much all icy surfaces, whether you're looking at a Jupiter Trojan or a comet or any other small body for that matter. And it's a nonlinear feature, which has stymied a lot of statistics in the past. And so I thought maybe we should just try and get rid of that. And so I invented what I call the reddening curve projection. It's really quite a simple idea. We reproject a two-dimensional color space into what I'm calling components 1 and 2, PC2 being the orthogonal distance from the reddening curve at its closest point to a given measurement, and PC1 just the line integral distance from solar color to the tangent on the reddening curve. And so if you go back and take the top panel here as an example, G minus R, R minus J, apply this correction and take a look at the projected colors, this is what you get. And it was really surprising to me to see that in PC1, there's basically no structure. It's pretty much just a blob of a continuum of colors. But in PC2, you can see very much a bifurcated distribution. There's two different peaks. And that bifurcation occurs at a PC2 of about value of about minus 0.15. And surprisingly, this same bifurcation occurs if you apply this projection to pretty much any other past optical near-infrared colors data set, whether that be hot sauce or emboss or Nuno Pacino's sample or whatever. You see the same bifurcation, and only the one bifurcation always occurring at PC2, regardless of which filters you're taking a look at. And so I would argue that, in fact, there's only two classes, and we actually only have evidence for two classes. Now, the one thing I haven't talked about here in this plot yet, remember I talked about the cold classicals as an example of a potentially unique surface. Those are the red points there. And as you can see, when you actually break down the color space correctly, you can see that cold classicals don't occupy a unique space at all. And this is in fact true of pretty much any dynamical class you can take a look at. We only see evidence for the BrightIR, what I'm calling the BrightIR and the FaintIR classes. And for reference, the BrightIR are the objects that track directly along the reddening line, and the FaintIR are the ones that fall a little bit below it and to the right. I'll very quickly just mention that with spectral modeling, we've demonstrated that you only need 2 classes. And so we adopt what we call the mixing model approach, where you create a class, and you theoretically create a class with 2 compositional components, something like a silicate which has roughly neutral colors and a red organic, and you mix the 2 together, and the relative mixture you get determines where you are along the color curve, like these dotted lines that you see here. And if you pick these 2 classes, which model only G minus R, and a spectral like what you see in the top right there, very much a toy idea, you can actually fully reproduce the full dynamic range of colors and the structures of the colors that you see for all filters that we've observed in the Kuiper belt. It's really quite amazing, actually, how well this works, given how simple the idea was. And so again, I think this is pretty strong evidence that you actually only need 2 classes, because you can account for the colors of 95% of Kuiper belt objects that we've observed. And so, and there you go, there are the 2 classes. And so going back to the toy idea we talked about at the beginning, the protoplanetesimal disk is actually, well, it's actually kind of boring in a way. From dynamical efforts, we know that the disk started at about 23 AU, because that's where Neptune was roughly born, or so we think, and then migrated out to its current position. And if you apply what we, our counting of the BrightIR and FaintIR classes to the dynamical models that best work, you can see that the dividing line between the 2 occurs at around 38, maybe 40 AU. And so between roughly 20 and 40 AU, there was actually only one kind of surface that came out. The compositions were actually quite homogeneous through that region. And that's really amazing, because there's a huge temperature range that can occur on a surface between 20 and 40 AU. And despite that huge range, the chemistry and compositions of the surfaces were quite homogeneous through that region. Another way to state that is, in fact, the disk was very thoroughly mixed. And I don't think this is something we quite anticipated. I personally thought there would be a lot more predicted dividing lines. And even also equally fun, if you take a look at the current orbital elements of Kuiper belt objects, you basically find FaintIR and BrightIR everywhere. When Neptune went plowing through the original disk to sculpt the Kuiper belt, it mixed everything up quite thoroughly. And so there really isn't one space where you find only FaintIR or only BrightIR objects. And I know I've been talking for probably longer than I should, so I'll throw up my conclusion splash and look forward to having questions. Thank you very much.
Hello, everyone. So I'm Maitrayee Bose from Arizona State University, and I worked with an undergraduate student, Ms. Victoria Fro, on this project, where we found this very unique and unusual micrometeorite, which has a composition and lithology that's similar to materials that are observed on Ceres surfaces. So to begin, the first question, of course, you would ask is, what is a micrometeorite? So micrometeorites are these tiny grains of cosmic dust, about less than 2 millimeters in size, that continuously rain down on us, on Earth. Approximately 800 to 2,500 tons of cosmic dust fall to Earth every year. And so just for comparison, the stack of a space shuttle composed of an orbiter, tank, and boosters has typically a liftoff weight of about 2,000 tons. So that's a lot of material that Earth receives in the form of these dust particles. Micrometeorites, we know, come from both asteroids and comets, and the ones specifically we found were collected from loose sediments on the summit plateaus of the Antarctic mountains, as is shown on the left. And so this is TAM for short. This represents a unique collection of very large micrometeorites, not observed in deep sea sediments. And of course, we love studying large micrometeorites because of their large sizes. They can be studied using a suite of laboratory techniques. So once we collect the sediments, we bring them home, right? And we pass initially this material through a sieve and heavily wash them so that we can get rid of any earthly contamination. This picture shows about 300 micrometeorites that have been neatly picked and placed on a glass slide, and we have a mosquito for scale. They're then embedded in a polymer and sliced and then studied using various laboratory techniques. So among thousands of such micrometeorites, we found this very rare micrometeorite, TAM19B7. It's one of the largest, about 1.5 millimeter sized, fine-grained micrometeorite. It shows minimal signs of heating during re-entry, which means that it preserved the original mineralogy and chemistry of its parent body. So my European collaborators, Martin and Luigi, used a combination of petrologic, mineralogic, and isotopic studies to show that this particular micrometeorite does not belong to any of the known classes of meteorites or even micrometeorites. Its highly aqueously altered lithology contains 97% by mass of clay minerals and possibly nanoscale carbonates. And so we decided to look for carbon in this very sulfur-rich and magnesium-bearing portion of this micrometeorite that I'm showing you here. So carbon has two isotopes. We have the carbon-12 and the slightly heavier isotope of carbon, carbon-13, which has one extra neutron in its nucleus. Carbon-13 is about 100 times less abundant than carbon-12. And we use the nanoscale secondary ion mass spectrometer at Arizona State University to measure these carbon isotopes in the reference standards and then the sample itself. So in this delta 13 plot that I'm showing you here, if we measure carbon isotopes in a standard, you would plot them as 0 point. So this line, this horizontal line here. When we measured the TAM19B7 sample, we found that this micrometeorite is actually carbon-13 enriched. And in fact, several parts of this particular particle were up to 4% enriched in carbon-13. Now, when we compared these enrichments in other extraterrestrial materials, we found something interesting. So cosmic dust also includes interplanetary dust particles, which are characterized by very fluffy textures. And they do not show these carbon-13 enrichments. When we look at meteorites, the bulk carbon-13 enrichments are also not observed in both ordinary chondrite and carbonaceous chondrite meteorites. So the only meteorite that shows these carbon-13 enrichments is this particular very unique meteorite, Tagish Lake, which fell in Canada in 2000, and it's rich. It's a carbon-rich meteorite, contains lots of phyllosilicates and also carbonates. The phase that contains these carbon-13 enrichments is actually the inorganic form of carbon. These are calcium and magnesium carbonates, and they're formed by aqueous processes. So the take-home point from this particular slide is that TAM19B7 micrometeorite has carbon-13 enrichments that are characteristic of carbonates and that form only via interaction with water. And so we speculate that it's a perfect analog to materials from highly aqueously altered Ceres-like asteroids. And so why Ceres? Well, NASA's Dawn spacecraft that acquired detailed imagery and data on the dwarf planet Ceres showed that Ceres is generally quite dark, as is shown in this image. Exceptions are those bright areas within the Occator crater that's rich in salts and carbonates. We think that subsurface briny fluids actively transport some of these materials from the deeper inside, and this has been happening in the last few million years. And so these are very young features that we're observing on the surface of Ceres. So to end with this slide, ocean worlds are extremely diverse, and they fall on this spectrum with very simple ice rock mixtures, as is observed or as is argued for Callisto, for example, to being differentiated, as is argued for Europa. And NASA has plans to, of course, visit Titan and Europa, as we all know. But we, in my team, along with Julie Castillo-Guest from JPL and her team, we advocate for a sample return mission from Ceres to bring back some of these bright, salt-rich, carbonate-rich material from Ceres mostly because these materials are highly sensitive and they can only be probed under laboratory conditions. So on a closing note, my team will continue to look for associations with pristine micrometeorites that are available in our collection. Thank you.
Hello, I'm Cristina Thomas from Northern Arizona University, and I am the lead of the DART Observations Working Group, and I'm here to tell you about our latest results. You can see a number of the prominent co-authors on the bottom of my slide, because I really want to stress that this was very much an international effort. So a couple of quick things about the DART mission itself. Here you can see a diagram of the mission. We are going to impact the satellite of the Didymos system, that's Dimorphos, sometime in late September or early October of 2022. Right now we're on track for launch later this year. And one of the key parts about this mission, at least from an observations point of view, it is a level 1 requirement number 3 here. And so you can see that is to measure the period change. And so DART is NASA's first planetary defense mission. It's a kinetic impactor to deflect the orbit of an asteroid. And so we're going to change the period of that satellite around the primary. And we need to know the answer to this period change to within 7.3 seconds from ground-based observations, both before and after impact. And so really the takeaway point here is that we need to understand the Didymos-Dimorphos system right now in its pre-impact state before we change it. And so we understand the orbit of the secondary Dimorphos about Didymos by looking at what's called mutual events. And we get this information from the Lightcurve. And so in this animation, you can see Didymos here and Dimorphos, the moon, coming around as it orbits the primary. And on the bottom, you can see a composite light curve of what this could look like. And so you have time along the bottom axis and brightness. And so when you can see both objects, you're going to get the most light from the system. But when one shadows the other, or one goes in front of or behind the other, you're going to get a dips in the light curve. And these are called mutual events. And so we understand all of the information that we can about the light curve of the system from everything we understand about the system, we understand from the light curve itself. And so this light curve contains 3 pieces of information. The first being the mutual event of the objects as it shadows or passes in front of the other. And that tells us about the timing of the orbit itself. We can kind of think about Didymos-Dimorphos as some sort of clock telling us what the orbit is, as we can use the time from one passage in front of Didymos to behind it. In addition to that, in the light curve, we also have the rotational periods of Didymos and Dimorphos. For the most part, we can actually only study the rotational period of Didymos, but we are hoping to be able to study Dimorphos itself sometime next year. And so each of these light curves is generated from a series of individual observations. And so here you can see an animation of Didymos in the center of the frame moving through a field of stars. And this particular animation is stitching together a series of images that was taken at the Very Large Telescope in Chile in early 2019. And so we have a large number of observations just like this, where we're taking observations of Didymos with the surrounding field of stars and looking at how bright it is with respect to those stars in each individual observation. And so we recently had a large observing effort in 2020, 2021, starting in December and going through March, with one key observing goal, and that was to better constrain the Didymos orbital position at impact. So where was Dimorphos going to be with respect to Didymos at the point of impact? If we looked at our data from 2003 to 2019, we found orbital solutions with an uncertainty on the position of Dimorphos, the satellite, at the time of impact to be plus or minus 65 degrees. degrees. And so here is an image of showing approximately what that error would be in the orbit, kind of this red line here for Dimorphos around Didymos. And it turns out that if you think about this in terms of a fraction of the orbital period itself, that error in position is something like 4 hours. So there's a 4-hour uncertainty with that previous data as to where when Dimorphos would actually show up at the exact position that we wanted to have an impact. And so we really had to improve that position for the mission itself. And of course, this was also the last chance to observe the system before launch and before the observing window that is associated with the impact itself. And so using our observing data from late 2020, early 2021, we were actually able to reduce that uncertainty to plus or minus 10 degrees in the orbit. So you could see that we were really able to reduce that uncertainty region here as shown by the red line. And this gives us an error in position of something on order 40 minutes, which is much, much better than 4 hours where we were before. We also know the orbital period of Dimorphos to within 0.1 seconds now. And we're hoping to do more observations in the few months pre-impact where we're able to observe to really cut down these uncertainties even further. And so here is one example of data from our data set. And so here we have the Lightcurve on the top. You see, as I mentioned, there are 3 components. We have the mutual events, we have the rotational period of the primary and the rotational period of the secondary. And I show this primarily for this middle panel here, which is separating out the mutual events themselves. And so you could see these dips in the Lightcurve, and these dips are correspond to very specific kinds of events. And so you can see how they have different shapes and different depths. And so this depends on whether or not we're talking about something passing in front of the other, whether or not there is a shadow event that's happening, and whether or not the primary or the secondary is the one that's passing in front of the other. And on the bottom here, you can also see the Lightcurve of the primary Didymos in the same set of observations. And so to conclude, I just want to look forward to 2022 when we are going to be thinking about the impact itself. And so again, we're going to be observing for about 3 months before the impact, and then we have a long observing effort after the impact. And so our planned observations for 2022, including further reducing the errors prior to impact, but also we're going to be doing all new Lightcurve observations after impact to find the orbital period change. And we're very excited about that. We also have planned observations, including guaranteed time on JWST at impact and afterwards for composition. We have an HST proposal selected, the PI being Zhanyang Li, for impact ejecta studies. And so hopefully we'll be observing at impact then as well, and then doing follow-up to see as the ejecta trails away. And then I do want to point out here that the Didymos system will be over 60 times brighter near impact than it was in all of our past observations for the past several years. And so that's really going to open up a lot of opportunities for detailed analyses of the system through the light curves. And so if you have any questions, please send me an email. I am Cristina.thomas@nau.edu. Thanks.